All right, here we go. So, quick video on section 6.5, 6.6, complex numbers, the complex plane, talking about trigonometric form, graphing them, absolute value, that sort of thing. So I just got basically two problems. This problem is first one, we're going to plot the complex number, find the absolute value for -4 plus 2 root 3i. We're going to plot the complex conjugate. We're going to write the trigonometric form of this complex number. And then, for a different complex number, we're going to write the standard form for a complex number that is in trigonometric form. And we'll talk a little bit about that as we go through it. So, let's get started. Plotting the graph, or sorry, plotting the number. So we have -4 plus 2 square root of 3i. The complex plane is like the regular coordinate axes, but instead of the x-axis, we have the real axis, and instead of the y-axis, we have the complex axis. So real numbers are like our x's, complex numbers are like our y values. So if I want to graph this, it's a -4 is my real number, 2 square roots of 3 is my imaginary part. So -4 is the real part, 2 root 3 is the imaginary part, and I'm just going to sketch where this is on the coordinate plane. So I'm going to go 1, 2, 3, 4, -4, and then 2 square roots of 3 is going to be, oh boy, what is that? About 3.4, 3.5-ish. 1, 2, 3, 4. I'm just going to double check it on the calculator just to get an estimate. 2 square roots of 3 is about, 3.46. So I'm at -4. I'm just going to estimate here. -4 comma 3.4 or 64, 46-ish there. So that's 2 root 3. That is this point plotted on the complex plane. Right? The real part is like your x, the imaginary part is your y. And sorry, this shouldn't be a complex here, this should be an I for imaginary. My bad. Complex numbers have a real part and an imaginary part. Together they make a complex number. Anything on this plane with the real and imaginary is a complex number. All the real numbers, just like 5, would just go on the real axis. Okay, let's now plot the complex conjugate for this number. So remember, the complex conjugate is, if I have a plus bi, the complex conjugate is a minus bi, right? So since it's -4 plus 2 root 3, I'm going to do this in a different color here. Let's go blue. The complex conjugate is going to be -4 minus 2 root 3i. So in other words, it's still at -4 for my real part, but it's going to be down here at -4 comma -2 square root of 3. Right, it's this point right there. And you'll notice the point and its complex conjugate are reflections over that real axis, right? Because the imaginary part changes sign, right? The complex conjugate of -4 minus 2 root 3i is -4 plus 2 root 3i. So these are conjugates of each other. If you're given one with a negative imaginary number, conjugate is positive imaginary part. If it has a positive imaginary part, then the conjugate is a negative imaginary part. Okay, cool. Let's write the trigonometric form for this point now. All right, so trig form. The trigonometric form, oh, I didn't find the absolute value. My bad, sorry, absolute value. We're gonna need the absolute value to write the trig form. So I'm just gonna go ahead and say trig form. So for some complex number, let's call it z, the trigonometric form is the absolute value of z, which we will find, we call that the modulus, times the cosine of the argument plus I sine of the argument, where theta, the argument, is the direction angle for this point. So basically, instead of saying we have like this real and imaginary part, we're saying we have an angle here, a direction angle from the positive real axis, excuse me, the positive x-axis, right? And then going counterclockwise, just like on the unit circle, right? That same angle idea. And remember, on the unit circle, the cosine of the angle represents the x-coordinate, the sine of the angle represents the y-coordinate. That's why we have cosine theta and then I sine theta, because the y-axis here is our imaginary axis. So if I want to find the trigonometric form for -4 plus 2 root 3i, I need the absolute value of z, and I need the direction angle. So I'm going to talk about the absolute value now. So let's say this is z. The absolute value of z is just this distance here, right? And it's just going to be using the Pythagorean theorem. It's the square root of -4 squared plus 2 root 3 squared. Right, so this is square root of 16 plus 4 times 3. Right, I'm squaring the -4, that's 16. I'm squaring the 2, that's 4. I'm squaring the root 3, that's 3. 16 and 12 give me 28. I can simplify that root 28, because 28 is 4 times 7. If I square root 4 and I square root 7, I get 2 square roots of 7. So here, absolute value equals 2 square roots of 7. Sorry, I missed that on that one. All right, and that's what we're going to use in our trig form. We have z equals, so here we can represent it as -4 plus 2 root 3i, or I can say 2 square roots of 7 times, and then I'm going to go cosine of some number plus I sine of some number, where that number is going to be my direction angle, and usually it's going to be in radians. I think on the homework both of them are in radians. It'll say like 0 less than or equal theta less than or equal to 2 pi if it's radians. It'll go 0 to 360 if it's in degrees. So make sure you're looking at that in the instructions. So here we're going to go radians, and we're going to round to 2 decimal places. All right, so the way to find this is I'm going to look at this triangle right here, and I'm going to find alpha, which is my what's the word for that? My reference angle. Sorry, reference angle alpha. So basically, I look at this right triangle where I have 4 and 2 root 3. I'm just using the absolute value of the x and the y. I want my angle alpha here, so I'm going to go inverse tangent of the opposite over adjacent. So tangent inverse, or arctangent of, oh my goodness, that should be a 4 of root 3 over 2. Square root of 3 divided by 2. And we get, make sure you're in radian mode. Get about 0.714. Seven one 3724 ... 71372 ... That's alpha. So this alpha, this arctangent of opposite over adjacent, gives me my alpha. Because I'm in quadrant 2 here, theta, my direction angle, the argument of the trigonometric form, is going to be pi minus alpha. It's going to be my theta here. Remember, if we're in quadrant 3, it's going to be pi plus alpha. If we're in quadrant 4, it's going to be 2 pi minus alpha. If you're in degrees, you just substitute 180 for pi or 360 for 2 pi. So here I go pi, and I use a different calculator. There we go. We're going to go pi minus what we just got there. And we get about 2.4278. So theta is about 2.43 radians. And that's what I'm going to put for in my cosine and sine. 2.43, 2.43. And this is my trigonometric form right here. The trigonometric form is always going to be absolute value times cosine of the angle, the direction angle, which we call the argument, plus I sine of that direction angle, which we call the argument. And the other name for the absolute value is the modulus. Sometimes you'll hear it like that. All right, now we're just gonna write the standard form for a complex number and call it good for that. Hopefully this video isn't going too quick for you. We're doing it between classes, so I gotta be a little bit quicker. All right, so if I have a trigonometric form like square root of 32 times cosine 150 degrees plus I sine 150 degrees, what I want to do is I want to write this in standard form. Which is the A plus BI form. So I'm just going to distribute this root 32. So it looks like number plus number times I. So I get square root of 32 times cosine of 150 plus, I'm going to move the I to the end here, root 32 sine of 150 degrees times I. This is my A value, this is my B value for my standard form. I want to simplify it though. 150 degrees is right here, right? 150, that means I have a reference angle of 30 degrees, which means cosine is going to be negative root 3 over 2. And the sine is going to be 1/2. Yep. So I have root 32 times negative root 3 over 2 plus root 32 times 1/2 times I. I want to simplify this, so I get square root of 32 times root 3, which is going to be square root of, oh goodness, 96 over 2. I don't know if we can simplify that any further. No, we can't, because that's 2 to the 5th. That's a 3. It's a negative, because it's negative. And then plus root 32 over 2I. That would be our standard form. Now, sometimes, if this was, and this was poorly done on my part, if let's say we had just square root of 30 instead of square root of 32. Say if I had root 30 cosine 150 plus I sine 150, if I picked a better number for this, right, it'd be square root of 30 times root 3 over 2, negative, sorry, plus I times root 30 times 1/2. The square root of 30 times the square root of 3 would give me square root of 90 over 2, and I could simplify that to 3 square root of 10 over 2, right? Because that square root of 90 is the square root of 9 times the square root of 10. You got to kind of watch out for that a little bit for simplifying. Is there a perfect square that factors out of this number inside the square root? There isn't for 96 or 32. I'm just going to double check that 96 to make it. I know it's right, but I just got to double check it. Yeah, it's good. Oh. Sorry. So we got to double check, hey, that root 96, can we simplify this? Yeah, we can. My goodness. Silly me. If we think, what divides into 96? 16 divides into 96. Right, 16 divides into 32. So square root of 32 is really square root of 16 times square root of 2. So it's just 4 root 2. This should really be a 4 square root of 2. So I'm going to get negative square root of 4 root 2 times root 3. So it's going to be 4 square root of 6 plus 4 root 2 over 2. And now I can simplify the 4 over 2 to just get a 2 root 6 plus 2 square roots of 2. And that's just because, and sorry for this root 32 can be simplified down to 4 root 2. So when I multiply by, right, the root 2 times the root 3, I get root 6. 4 divided by 2 is 2. Keep the negative. 4 divided by 2 is 2. And then that square root of 2 just hangs out. So, sorry, this was poorly done for video. Hopefully it's still helpful. The big idea going from trigonometric form to standard form is you multiply through by that modulus and just simplify from there. Where this piece, this times the cosine gives you your real part, this times the I sine gives you your imaginary part. All right, hopefully that helped. I got office hours. Let me know if you have more questions, and good luck on the homework.